Adding and subtracting vectors. We talked about vectors yesterday in terms of how we can read them. And they're basically, they are give magnitude and direction. It's a scalar, it just gives magnitude. 25 miles per hour is simply a scalar. 25 miles per hour going east is a vector. We get how fast it's going as well as the direction it's going. 90 degrees at 200 miles an hour. Well, not only this is a trigonometric function, but not only are we knowing how fast it is, but we also know the direction it is by 90 degrees. So we can add and subtract vectors, and we use this in physics. While this is an XY coordinate system, remember, when we determine a vector, that's where the endpoint is, and that is from the origin. So if I have right here, I have two vectors, 4 comma 5, and you can see here is the first one. I go 4 across, like this, 5 up, 4 comma 5, and the second one is 8 comma 2, and that is, there's 8 right there, up 2. Let me erase that. We can add those together. Now, we could simply add it by just putting the 4 and the 8 together and the 5 and the 2 together. But what's interesting about vectors is we are looking at quantities that physically can be defined. And if I add this, I'm calling vector V, the one that starts at the origin, 0, 0, goes to 8, 2. I take that same distance, same direction, I move it up over here. And it's the same angle, by the way, if you notice. It is 8 across, 2 up. If I go here, I go 8 across and 2 up. I get 12 sevenths. No different if I add the 4 and the 8, the x component and the y component together. And remember, we can also write this in columnar format, 12, 7. And that is 12 for the x, 7 is the y coordinate. Here's another one. I'm going to add vector v to vector u. Vector v is 6, 3. You can see right here, I go 6 across, 3 up. And vector u is 1, 4. And that is 1 across, 4 up. And, let's see, erase this here. Doesn't get too messy. And if I go back and I look at this, I can move this. This is, remember what I said, 6 across, 3 up. If I just go 6 across and 3 up, there's my answer right there, 7, 7. No different if I add these two together. 1 plus 6 is 7. 4 plus 3 is 7. So we can physically prove this on a graph as well as mathematically add together. And again, columnar format, that would also be 7, 7. And by the way, we could also go in the reverse situation. Let me erase what I've written over here. And what's interesting is vectors, when we're adding, work in the same direction. Instead of adding vector v to vector u like I did, if I add the vector u to vector v. So here's my vector v. It ends here at 6, 3. And remember, vector u was 1 and 4. So I'm going to go 1 across, 4 up. And guess what? I get the same result, which you would expect. Now, this is the triangle method. This uses one side. And what's interesting is when I do this, I can look at this. Negative 7 plus negative 4 equals negative 11. Negative 2 plus negative 5 is negative 7. And I could have done it like this by putting this right here. Or I could have done this, taken this one, and put it right there. And either way, I get negative 11, negative 7. Or as in columnar format, as I've shown to the right here. negative 11 over negative 7. Again, this is making a triangle of one with the other. And we say it's a triangle because this line of symmetry down the middle here, this is symmetrical on both sides here. Doesn't matter which direction I'm going. Now, when we are subtracting, we are putting one tail going the opposite direction that originally was going. When we added the vector, if I got vector u at 6, 8, this is right here, 2, 4, 6, 2, 4, 6, 8, and then here's vector 9, 5, vector v, 1, 2, 3, 4, 5, 6, 8, 9, and there's 5. And if I'm going to simply add those up, I could add 6, 8 to 9, 5. Let's go 6 across, 2, 4, 6, and then I would go 8 up. 2, 4, 6, 8, and end up being there. But notice it's subtracting it. We don't want that. We don't want the additional. We want the subtraction of it. Which, notice I always put the tail on the other tail. And what I'm going to do here, when I subtract, I'm not putting the tail on the other tail like this one. That's adding. We have to take whatever direction this is going. It's still parallel here. Notice this line is parallel, but I'm adding the tail going in the opposite direction. This is going in this direction, my original V. My negative V is going 180 degrees right here. So, and notice it's the same angle right there as this one. They are parallel, but it's going in the opposite direction. And I add to the tail of the first one. And why am I adding to the tail of the first one? Because the equation is asking me to say, what is the difference u minus v or v minus u. So if I go u minus v minus u, I'm going to put v in the opposite direction. And get my little red pen here. There's a pause there. Lost my pen for a second. Notice this is still, if I go 9 across and 5 up, I'm going the opposite direction. So I'm going to go 9 in this direction. That looks like it's 2, 4, 6, 8, 9. And then 5 down. And that's where it ends up right there. So, or I could, let's look at this. What if I had u minus v instead of v minus u? Let's erase this here. If I had v minus u, my u is going, let's see, 6, 8, so it'd be minus 6 minus 8. So I start my v here, the end of my v vector, and I'm going to put the tail of my u in the opposite direction. So it'd be minus 6, 2, 4, 6, minus 8, 2, 4, 6, 8. So it end up doing that. Now, I'm not the best artist, obviously, but you can see, again, this is parallel to that, but they're going in the opposite directions. So there is a difference between u minus v and v minus u. And so a different thing, 5 minus 3 is different than 3 minus 5. 5 minus 3 is 2, 3 minus 5 is negative 2. So when we're subtracting, we are getting different results. And remember, whatever vector we're subtracting, we're putting the x and y component, which is the horizontal and vertical component, in the opposite directions for both of them. Now, this is called the z method, which is what we were doing basically. And what are we subtracting? We got u, vector u here, and I got vector v. Vector u, looks like I put 2 v's there, and I apologize for that, is negative 4, 12. So this is going to be negative, let's see, that's negative 4, 12, and there's this vector right here. That's vector u right there. And then here's vector v. So we've identified them, and we want to subtract v from u. So we're going to call that new one z. So I know I'm looking at this vector here. I am going negative 5, 10. That's the original distance from the origin. Or I say the direction, excuse me, the direction of the origin. So I'm going to go 5, negative 10. I'm going to go the diametric opposite, 5, negative 10, starting at the head of that u. So if I go 1, 2, 3, 4, 5, then I go minus 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And we're going to call that one z. And where does it end up? It ends up at 1 comma 2, but it doesn't start at the origin. It starts at the head of that vector u. Now, we can even do this with, as I was alluding to earlier, trigonometric functions. The cosine of 80 degrees, remember, cosine is adjacent over hypotenuse. And if I got a distance of 9, and this is the hypotenuse here, because remember, if we use trigonometry, oh, that is a terrible straight line. Let me erase that. I'm trying to draw the right angle here. No, it's not much better. But there's my right angle there. And I can determine, let's erase this out of pure embarrassment. I can determine with directionality vector which has a hypotenuse of 9. And then I can determine the x component and the y component of it. Because remember, cosine is adjacent to hypotenuse. Remember, the cosine is along the x-axis, and the sine is along the y-axis. So when I do this, I can actually use vector analysis with trigonometry. 80 degrees, the cosine of 80 degrees, remember, cosine is adjacent to hypotenuse, and I've got a hypotenuse of 9. So the cosine of 80 degrees is 0.173648. I multiply both sides by 9. Multiplication here. Guess what? That crosses off. 9 times 0.07 is this right here. This equals x. Multiply 9 times 0.017348. I get 1.56. So my x component is 1.56. That looks about right, actually. That is but about 1.5, because here is 5 right here along the x-axis. And then the sine is opposite of our hypotenuse. I'm doing the same thing. Multiply both sides by 9. And here's my 9. Sine of 80 degrees, 0.94841. These cancel out. I'm left with x here. And my x is 8.846. And that looks about right, too. Here is 5 on the y-axis. Here's 8. It's almost 9, 8.846. Not quite. And so I could say when I have a trigonometric function that's hypotenuse of 9, we'll call it vector A, it in columnar format is 1.56, 8.86. Remember, and this is the x-axis, and this is the y-axis. We can still do directionality. And remember, when we have the unit circle, that's 360 degrees all the way around, or 2 pi, as we've studied before repeatedly. I'm going to put in my calculator cosine of 340 degrees, and because I have got, according to this, I have got a hypotenuse of 10. That distance is 10. So I know my hypotenuse. And cosine of 340 degrees, 0.9397. Do what I did before. Multiply both sides by 10. The 10 in the denominator cancels out over here. I'm left with x equals 10.9397, which is 9.4. So this distance right here. Here's 10 right there. This would be 9.4. 9.4. We'll do the same thing with the sine, which is opposite of our hypotenuse. And that's going to be the sine of 340 degrees, 0.3420. Multiply both sides by 10 again. That'll cancel out the 10 in the denominator. Over here, that's a terrible 10 up there. Sorry about that. And that's 10 times 0.3420 or negative 3.42. And I get, is it should be a negative. The sign of the already is negative 0.34. And what I get here is that should be a y too, a y-axis of negative 3.42, which looks about right here. This is 2, here's 4. It's about a little over 3, but not much more. So yeah, it looks like it's about 3.5 right there. So my vector A is 9.4 on the x-axis, 3.42 on the y-axis, and that column, negative 3.42, is column format is written as 9.4, negative 3.42.